All right, welcome everybody to Module 2, Lesson 3. This one is on electron configuration, which may be a little bit longer than the past one. So let's get to it. We'll start with Erwin Schrodinger. That name might be familiar to you if you've ever heard of Schrodinger's cat. If you don't know it, Google it. It's interesting. But he developed the quantum mechanical model. This model determines the allowed energies an electron can have and how likely it is to find the electron in various locations around the nucleus. Okay, so we have the principal quantum number, which is n, shows the energy level and the size of the orbital. So as, hopefully it makes sense to you, as we get to more energy levels, like I showed you previously in the last video, as we get in the number of energy levels, now we know this isn't what it really looks like, but this is a good way to visualize it. You can just see that the size of it is getting larger. The atomic orbital is the region of space with a high probability of finding an electron. So it says S, P, and D are the most common orbitals, but there are others. And the other one, we are going to talk about all four of them, S, P, D, and F orbitals. And I'm going to have a link to this website, the Orbitron, where it can show you the computer-generated models of the different orbitals. I'm going to draw them for you here in a second, but looking from the computer ones is a lot more interesting than my very bad drawings. And then we know the electron cloud is just the area of uncertainty where an electron could be. It says the closer to the nucleus, so the higher the probability of an electron being present, which hopefully makes sense to you because the electrons are negatively charged, the protons are positively charged, and so they're going to be attracted to the nucleus, and so they would more likely be closer to the nucleus. So let's look at those different orbitals. S orbital, P orbital, and the D orbital are the ones you should be able to recognize. An S orbital, that's the nucleus. It's just a sphere around the nucleus. A p orbital, if this is the nucleus, it's like an infinity sign, or like a bow tie. And remember, this is in 3D, so it can like rotate. Again, this part right here, the dark part, the circle is going to be the nucleus. And then the d orbital, again, if that's the nucleus, it looks like a 4-leaf clover. So those are the different orbitals that you should be able to recognize their shape, because shape will come into play when we talk about our periodic trends. Okay, Heisenberg, if you've ever watched, I don't even know what that show is because I never watched it. That's a name you should recognize. The Heisenberg uncertainty principle says that we cannot know both the position and the velocity of a particle at the same time. So when you try to find out where it is, you do that by putting a beam of energy in it. You can figure out where it is, but now you don't know how fast it's going because you've just put more energy into it, and vice versa. The electron configuration shows the ways in which electrons are arranged in various orbitals around the nucleus, the nuclei of atoms. There are 3 rules. So how these notes go is there's a lot of individual things that we have to talk about before we can put it all together. So if some of these individual things don't make sense currently, they will when we put them all together at the end. So 3 rules. The Pauli exclusion principle says that an atomic orbital at most may hold 2 electrons. Hund's rule states that the most stable arrangement has the most parallel spins. Again, we'll talk about what all these things mean. Authbah Principle states that electrons fill the lowest energy orbital available. Now, before we do this, we want to talk a little bit about valence electrons. Valence electrons are electrons in the outermost energy level. And those valence electrons help us determine how an atom will react. An easy way to show valence electrons is to go into and draw a Lewis dot structure. So first off, let me share a periodic table with you, and so we can talk about what are valence electrons. So how the valence electrons work. This column right here, this first column, 1 valence electron, 2 valence electrons, 3 valence electrons. Notice we skipped all these things in the middle. 3, 4, 5, 6, 7, and then the noble gases here all have 8 valence electrons. Okay, so those are how we figure out our valence electrons. So if we go back here, our first example is carbon. If you look at your periodic table, which you should have in front of you or have one near you, carbon has 4 valence electrons. Now, the easiest way to do a Lewis dot structure, I just start at the top and draw my dots. And you want to make sure they look like dots and they look like they're meant to be there, except for instead of like, oh, that's supposed to be an electron. No. So we got 1, and then we go around clockwise, and each side gets an electron before you go and pair them up. So in carbon, it has 4, so that's going to be its Lewis dot structure. So the 4 electrons starting at the top, working around in a clockwise position. You don't have to go clockwise. You don't have to start at the top. It does not matter, but each side needs to get an electron before you go back and pair them up. Barium, 2 valence electrons. 1, 2. Okay. Chlorine has 7. So I'm going to 1. Okay. Work with me here. 2, 3. I'm sorry, these don't look like dots, but you get the point. 5, 6, 7. So you have 3 paired electrons and then 1 unpaired electron. Oxygen has 6. 1, 2, 3, 4, 5, 6. Arsenic has 5. So we got 1, 2, 3, 4, and then we can pair them up 5. Very simple. So I just want to look at real quickly, how do you do, so these are individuals, what does it look like when you're trying to form a compound? Okay, well, let me show you. Let's say we want to do the compound CH4. Okay, so you've got 1 carbon, 4 hydrogens. So hydrogen has 1 each. Carbon has 4. Now, in order to be happy, electrons, they want 8 valence electrons. So they want to look like a noble gas. So in order to do that, what happens is that we share electrons. We share electrons to make that happen. We'll talk more about this in the future, whatever. But hydrogen, it only wants 2 valence electrons. Okay, it's very happy with 2. It can only hold 2 because it only has a first energy level. So what happens is that these guys, they end up pairing up because we don't want any lonely electrons. And so then what happens is now you have the hydrogens and the carbon sharing their electrons. And now you can see carbon has 8 total valence electrons and hydrogen has 2 for each one of them. Let's do a different one. Let's do water. So what you should do, I know these are pretty easy, but you can start by counting up all of your valence electrons. 6 and 2 gives me 8 valence electrons I'm working with. So I'm going to have my oxygen with their 6. And then you can see, okay, I have 2 hydrogens. And then basically, these hydrogen is going to pair up with one of the lonely oxygen electrons to get, again, it doesn't really matter how they go. We're going to talk shape later on in the year. These look like eyeballs, not dots. So there you would have the Lewis dot structure for H2O. Let's do one more, because I think there are practice in your homework where you do an ion. So ions are a little special. So let's see here. So what we're going to do, count them all up. 5 plus 4. Nitrogen has 5. There's 1 for hydrogen, but there are 4 of them. Now, when you are a +1, that means you lost 1 electron. Remember, if you were -1, you gained 1 electron. So here we're going to -1. So 5 and 4 is 9, -1 is 8. So I have 8 electrons to work with. So I'm going to take nitrogen. 1, 2, 3, 4, 5. Now I'm going to lose 1. So the easiest way to do this, I'm just going to lose that one. I mean, the hydrogens only have 1. And so then I'm going to just bond my hydrogens here. Now the nitrogen has 8, each hydrogen has 2. And to do this, the special thing about an ion is when you're done, you have to put it in brackets with its charge so that we know that it's an ion and that it either lost or gained an electron. This is just a very brief introduction to electron configuration. In the bonding unit that we will do, we will go more in depth on electron or on Lewis dot structure. So this was just a very gentle introduction, and I'll include extra videos if you're confused. Okay, so now we have to look at our periodic table and talk about where are our orbitals located. So there are the S orbitals, the P, the D, and the F orbitals. So I don't think I can do different colors on here, so I'm just going to circle them. So this part right here, plus this, that is the S orbital. These are the S orbital electrons. Okay. In the completed notes, they should be in color and highlighted different colors, so you should be able to see it better. So that's the S orbital. This one right here, this is the P orbital. Okay. This middle chunk here, this is referred to as the D block, or where the D orbital is. And this part in the bottom, this is the F block. So this is the block of where the F orbital is, the outermost part. Some important notes, the S orbital can hold at most 2 electrons, P orbital 6 electrons, D block, D orbital 10 electrons, F block 14 electrons. How did I get that? Just count 1, 2. 1, 2, 3, 4, 5, 6. So it can hold 6 electrons. Trust me, for the D block and the F block, it's 10. Other important things, and again, remember, I'm just throwing all of this information and then we're going to put it all together. For the D block, whatever the energy level is, whatever it says it is, you take away 1, and that's what it actually is. And for the F block, you take away, which is N, which is that energy level, -2. Okay, and again, I will go through this and show you what all of this means. You can use this. It tells you the order to go on the periodic table, but the way I'm going to show you, I think is easier. So now it's time to put all of these things together. And so there are 3 different types of electron configuration. There's the complete electron configuration, the noble gas core configuration, and the orbital diagrams that we're going to have to do for each one. I'm just going to go over a couple of the examples, and then you can see what the other examples, the answers are. You can try them yourself and then look to see if the answers are correct that you got. So we'll start with silicon. The first thing you should do is find it on the periodic table. It's Si. If you find silicon, you'll notice that there's 14 electrons. So what we do, let me share a periodic table. So here is silicon where I want to be. Right here. So the easiest way I find to do this is you start at the very beginning of your periodic table, work down and around until you get to the element that you're looking for. So on your periodic table on the left side, these are the energy levels, okay? I know your periodic table doesn't quite look like this, but these are your energy levels. And then these, remember, S orbital here, P, D, F orbital. So the way this works, we do, I guess I can do this. It goes energy level. I'm writing in the corner if you can see. Energy level, and then orbital, and then number of electrons. So we'll start here. Right here, first energy level, so I'm right here at hydrogen. First energy level, so I'm going to write a 1. It is the S orbital. And remember, the S orbital can hold 2 electrons at most. In order to go to the next part, the next orbital, you have to be full. So you can't move on to your next part until you're full. It's full with 2, so I'm going to write 2, and then that's it. Now I can keep going. If we go down, will we go over? Okay, that's it. So now we go to the next part, which is right here. Now I'm in the second energy level. And then you can see here, this is again the S orbital. And I need to go further than this part right here. I need to go all the way over here. So I need to be full and put a 2 here. Okay, so 1s2, 2s2. I'm not done, keep going. I haven't gotten to the element that I want. So now I'm here. I'm still in the second energy level, but now I am in the p orbital. And there are 6 electrons there. So 1, 2, 3, 4, 5, 6. The p orbital can hold 6 electrons. So 1s2, 2s2, 2p6. Now I'm go down and around. Now I'm over here. Now I'm in the third energy level. This is the s orbital. The s orbital, I'm almost to where I need to be. I'm not there yet, so this needs to be full. So a 2. Move down, down, down. Now I'm over here. I got to write below, but this would just keep going. I'm still in the third energy level, right here. I'm in the p orbital now, and then I just count to see how many electrons I get until silicon. So 1, 2. So it's going to be 3p2. And that is your electron configuration, the complete electron configuration for silicon. Okay. So let's go back here, and I'll rewrite this here. 1s2, 2s2, 2p6, 3s2, 3p2. Wonderful. That's the complete. Next is the noble gas core configuration, which is a shorter way of doing it. Looking back at our periodic table, in order to do this, you have to say, okay, here's silicon. Tell me the noble gas, because it's the noble gas core configuration. Tell me the noble gas that comes before it. It's neon. So what I end up doing is I put neon in brackets, and then I just finish my electron configuration until I get to the element I'm looking at. So to finish it, that's 3s2, 3p2. And that would be the noble gas core configuration. So brackets NE, 3s2, 3p6. Oh, no, not 3p6, 3p2. Okay, so you'll notice by putting neon in brackets, I've written this much out of my long electron configuration. And finally, we have the orbital diagrams. The orbital diagrams are a more visual way of seeing our electron configuration. So what we do is we draw boxes to represent our orbitals, okay? And each box, going back to our rules up here, each box can hold 2 electrons, the Pauli exclusion principle. Each orbital may, at most, describe 2 electrons. So each box we draw can hold 2 electrons. So if I was an s orbital, that's going to be 1 box. P, 3 boxes because it can hold 6 electrons. D is 5 boxes. And then F is 7. And we always, no matter how many electrons are in any particular orbital, always draw all of the boxes. So for silicon, I've got 1s. So I don't draw boxes because I think it's too much time and I can't draw a nice box. So I just draw a line and then underneath it, label it 1s. Draw another line, 2s. Now I'm at 2p, so I'm going to do 1, 2, 3 lines. I label the middle one, 2p. Then we have 3s, and you should keep going in 1 line, but I don't have enough room. 3p, okay? Going back to those rules, it said that the Authbah principle states that we have to fill the lowest energy orbital available. So we go in order of how we wrote it. And then Hund's rule says that we have most parallel spins. So when we do the Authbah diagram, we represent electrons as arrows. And so to have parallel spins, 1 arrow goes up, 1 arrow goes down in each box. It's nothing crazy. So 1s has 2 electrons, so I draw an up arrow and a down arrow. You always start with an up arrow. 2s, there's 2 electrons, so up and down. 2p has 6, so I'm going to go up, 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 down, down, down. And you may notice I do a single-headed arrow just out of pure convenience. 3s is there's 2, so up, down. And now here's where it becomes important. So in my 3p, I only have 2. Notice I have 3 boxes. So 1 box gets an up, 1 box gets an up. The last box is empty. And that's how you do your orbital diagrams. Okay. So I'm going to erase this so I can do the next one, the iron. But if you need to keep writing, just pause. So you can do that. Okay. So we'll do iron. I'll do all 3 for iron again, walk you through it, and then I'll ask you to do bromine yourself and check your answer in the completed notes. And then we'll do polonium on the next page because it's a long one. So iron, we know it's Fe. And iron has 26 electrons. So I'm going to go back to the periodic table. So let's see. Here's iron right here. This is where we need to get. Notice now we're in the d orbital. So then things are going to be different here. So let's go through, start at hydrogen. It works the same. I'm going to do it over here in the corner. So I've got 1s2 gets me to helium. I don't want to stop there. I want to keep going. 2s2 gets me to beryllium. Again, I want to keep moving, keeping all of these things full. Move over to, I'm right here now. That's 2p6. Oh, down, back around. Here now I'm in the 3rd energy level, the s orbital, 2 electrons. If I stopped right here, I'd be magnesium. I don't want to be magnesium. I want to keep going, still in the 3rd energy level. Now I'm here. This is the p orbital. That orbital has to be full because I need to go past it. Go down, back around. Now I'm here, the 4th energy level, the s orbital, 2 electrons because I need to be full. Now here's where we get into the d orbital. So this is where the d orbital starts. Okay. Remember I said whatever energy level it says it is, so it says it's 4, you take 1 away. So this is actually 3d. All right, so that's, and then we just count 1, 2, 3, 4, 5, and 6 to get us to iron. So that's your complete electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Noble gas that comes before is going to be argon. So I'm going to put argon in brackets. 'And then by putting it in brackets, I write this much. 2s2, 2s2, 2p6, 4s2, 3d6. Noble gas that comes before is going to be argon. So I'm going to put argon in brackets. And then by putting it in brackets, I write this much. 2s2, 2s2, 2p6, 4s2, 3d6. And then I just finish 4s2, 3d6. That's it. Now I'm going to go back here to the notes, and we're going to do the orbital diagram. I'm going to just rewrite it because it's so easy to do your orbital diagram if you have the complete electron configure written out. 2p6, 3s2, 3p6, 4s2, 3d, what did I say, 6. Okay, so now I'm going to draw my boxes, well, lines for me. 1s, 2s, 1, 2, 3, 2p, 3s, 1, 2, 3, 3p. Down here, here's 4s, 1, 2, 3, 4, 5. I got to draw 5 for my 3d. Everything's full up until the 3d, so you just go boom, boom, up, down, up, 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 down, 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 up, down, up, 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 down, 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 up, down. And now here's where, again, you got to pay attention. So up, 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 up. That's 5. Down is 6. There's your orbital diagram. Okay. So, yeah. So let's do polonium. Polonium, I'm going to do the electron configuration for polonium up until we get into the f orbital. So notice that polonium, where is it? It's 84. Polonium's right here. Here is where the f orbital starts. So I'm going to do my electron configuration up until barium. Actually, I'm going to write out the whole thing for you. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. All right, 6s2 gets me to barium. Now, how it works here, you go through the f, then the d, and then the p orbital. So it says I'm in the 6th energy level. If I'm in the f orbital, I take away 2. So that's going to be 4f. I go all the way through, gives me 14. And then I can go up 1 energy level because I'm n minus 1. So 6 minus 1 is 5. 5d10. Polonium's right here. So that's 6p, 1, 2, 3, 4. Okay. And you'll get practice with more of those. Okay. There are some exceptions to the rules because there are always exceptions to the rules. Okay. Chromium, if you look at it, it should be 3d4, 4s2. So in reality, chromium is argon 4s2, 3d4. But chromium becomes more stable when the d orbital has an electron in each one of those boxes. Okay, the d orbital is for stability. So the more that it can be full, the more stable it's going to be. Same thing with copper. Copper should be argon 4s2, 3d9. But what happens is one of those s electrons goes into the d orbital and makes that full, which makes it more stable. Lanthanum and actinium, they have their outermost electron is in the d orbital. So they go 2 in the s orbital and then 1 in their d orbital. Okay, last thing here, just a couple of vocabulary terms, para and diamagnetic. Paramagnetic elements that become magnetic when exposed to a magnetic field, and you can recognize them by having unpaired electrons. Diamagnetic, they are not affected by a magnetic field because they have all paired electrons. So in order to do this and figure out if an element's para or diamagnetic, The best way to literally see if you have paired or unpaired electrons is to do the Authbah diagrams. So helium has, it's just 1s2, so that's up, down. Those are paired, so that's dia. Beryllium is 1s2, 2s2. Up, down, up, down. That's paired, so that's dia. Lithium, 1s, 2s, so it's 1s2, 2s1. That's unpaired. That makes it paramagnetic. That's lithium. And then nitrogen, 1s2, 2s2, 2p3. Those all three are unpaired. That's paramagnetic as well. Okay, that is it for electron configuration. If you have problems, there's practice that you can do. There's going to be those extra notes that are below on the presentation page if you want to watch it. Somebody else explain it. It's very hard for me to do this like this. I can't gauge if you get anything or not. So that's where you need to ask your questions. I'll be available. Just let me know.